with the internet and its periphery. I mean, the major part of this talk is on internet access service and internet backbit service. That means on the transmission of the data packages, which creates a derived demand for this transmission of the data packages by internet application services. And they need, of course, the telecommunication infrastructure, local and long distance, terminal equipment, and also content. And when we start with this topic, we have this evolution of this internet. The traditional internet transports data packages on the basis of the best effort transmission control protocol, TCP, assigning all transmission equal priority as they pass along the network. And the best effort average traffic quality results endogenously, depending positively on capacity and negatively on traffic. That is this famous von Jacobson algorithm. You need not a network, the network carrier need not do anything. The speed will be decreased when dropping, when a resubmit packet comes, so that we have no congestion pricing or quality differentiation in this transmission control protocol. And due to the transition from narrowband access to broadband access, congestion and heterogeneous requirements for traffic qualities become increasingly important. And the starting point is neither best effort average quality networks nor best effort maximum quality networks can be expected to provide the necessary allocation mechanism. That is the major lessons also what John Kruse was already bringing here. Is also known from transportation economics that when you have really congestion problems, unlimited capacity cannot be an efficient, let's say an economic efficient solution. And let's say a kind of fairness criteria that to control, let's say to allocate capacity regarding to the per flow is also not efficient because it does not provide the, an efficient allocation mechanism. Let me go back to the definition of the concept of network neutrality. Generally, the term network neutrality is used as a regulatory concept addressing what deviations should be permitted from the traditional best effort internet. That is, when we read in the literature, the long, bigger literature, in the meantime, network neutrality usually is meant as a regulatory concept. And when we look at this, mandatory network neutrality consists of ex ante regulation of traffic management with reference to the traditional TCP, assigning all data packets equal priority as they are passed along the network, so that any deviation from this traditional TCP protocol will be considered should that be good or not from the regulatory point of view. And my point here is, what I really like to focus is, in contrast, market-driven network neutrality means an entrepreneurial search for traffic allocation in such a way that there are no incentives for the internet traffic service providers to discriminate between possible network applications on the basis of network capacity requirements. This is the case if any application is charged according to the opportunity costs of the traffic capacity it requires. Also from the economic point of view, also in other networks, usually we have the efficient allocation problem and we have the non-discriminatory problem, and we can combine these both. The incentives for non-discriminatory allocation of capacity is when we use it in an economically efficient way. That means that is my starting point of my talk, to contrast network neutrality regulation on one hand and the entrepreneurial search for traffic allocation taking into account the opportunity cost of traffic. Let me now start to look at the discriminatory potentials of the TCP in broadband internet. In the narrowband internet, the best effort TCP fulfills the criteria of market-driven network neutrality, since all applications are homogeneous with respect to transmission capacity requirements, transmission quality requirements, and transmission capacity. the TCP creates no incentives to discriminate between different applications in narrowband internet. In the broadband internet, with the capacity-intense and heterogeneous applications, the TCP creates large discrimination potentials. Low-capacity applications are discriminated against by high-capacity applications, and time-sensitive applications are discriminated against by time-insensitive applications. That has all to do with this TCP algorithm, which looks at every flow individually and is not considering the total amount of flows in a given time period, or whether you use different flows in the same time period. That is what Briscoe, for example, was also arguing that in a broadband network, that it's not so fair to have the TCP algorithm when you have such heterogeneous demand for traffic quality, transmission quality and capacity. So the next step is to think what is market-driven net neutrality in broadband internet. Market-driven network neutrality in broadband internet requires congestion pricing and quality of service differentiations. So first of all, it requires, when we have a broadband internet, we need to go away from this, let's say, from the allocation of the congestion from the final user, so that the speed of his sending packaging rate will be decreased when a resubmit or dropping occurs, and to have an active network allocation policy. One would be to have application restrictions, for example, limit multi-phase to multi-phase applications or voice over IP. But these applications do not take into account the opportunity cost for capacity usage, which is necessary to have the right economic incentives for all possible applications. For that, we need market-driven network neutrality in broadband, also congestion pricing and quality of service differentiation. And irrespective of how network neutrality regulation would be implemented in detail, it would limit entrepreneurial flexibility with respect to the design of internet architectures, traffic quality differentiation, and flexible transmission pricing. So that means that, in fact, the TCP protocol is not the good reference point to bring, let's say, market-driven net neutrality in the broadband internet. Now, the next step I would like to bring is what is now the role of congestion pricing on one hand, and let's say quality of service differentiation on the other hand. And what I would like here to bring is a model which I have. You have to give a sketch on it. That means market-driven network neutrality based on interclass externality pricing. The first step is, that is, I do not have the time to present here, when we introduce congestion pricing, that is what Mackie Mason-Ryan already did in 1995, or so this starting to think about congestion pricing, that was still on homogeneous quality. And the idea is now to combine that with heterogeneous qualities of transmission, to take into account the heterogeneous quality requirements of different applications. Congestion pricing combined with quality differentiation can be implemented within the internet architecture of differentiated services, DiffServ networks. Are different architectures possible to implement quality of service differentiation in the internet, but the DiffServ architecture has been widely proposed for providing quality differentiation due to its scalability. That is an architecture which can also be introduced in backbone networks. The DiffServ scheduler route offers a predefined number of traffic classes using a strict priority of schedule. Minimum number would be 2, 3 or 4 could also be there, could n number traffic classes. Marking is achieved by setting a specific traffic service code point value indicating the traffic class within the IP package header. That is possible to implement already. And traffic classes are monotone with respect to traffic quality. packets within a higher traffic class will experience lower delay and lower packet loss than packets within lower traffic classes. This already shows that that is not compatible with the TCP protocol. In the TCP protocol, you are blocked into, your machine cannot enter when you have high priority needs for transmission. So that is not compatible with the TCP protocol. And within a deep served domain, all packets belonging to a given quality of service class receive the same treatment. In particular, within one service class, no priority rule is applied. When we start to model congestion in deep-served networks, some assumptions are necessary. The allocation problem of an arbitrarily chosen traffic service provider under competition is analyzed. We have different traffic service providers. Because they are logistic networks, they are competitive. It's not that we have this local access infrastructure problem where regulatory market power may remain in some areas when you have not competing infrastructure access platforms. We have here different logistic possibility of different logistic firms, internet access service providers or backbone providers. And let's assume n traffic classes, which may be 2 or 3 or 4, whatever, what you think, what is good to differentiate. The packages are classified and grouped into different traffic classes. For example, red, blue, and green, that are the different packages are belonging to the same traffic class, I. In period T are denoted QIT, so that for I1 is the red packages, the high priority packages, 2 would be blue, the medium priorities, the green would be the third priority, and you have a tagging, so that when you enter the access service network, the packets are tagged, red or blue or green, and then we have the inverse demand for aggregate traffic in the traffic class I. That means PIT, depending on the number of packages in the class I, in the period T, is then the inverse demand, the derived demand, economically speaking, for aggregate traffic in the traffic class I. It doesn't matter what kind of final service, application service will we run on with these packages in the class. Depends only on the priority to have the single I would like red, high priority or medium or low priority. Capacity measured in bandwidth, total bandwidth W, whereby package flows of different traffic classes have access to all resources. We have only one bandwidth. One could also model separate bandwidth, but there are arguments to have multiplexing advantages when we have only one bandwidth, and rho W is the capacity cost. Now we have to differentiate between intra-class versus inter-class externalities, because the variable cost of transmission of a packet in class I in period T is KIT depending on Q1T until QNT. That means it depends not only on the number of packets on the same class, but also on the number of packets in the other classes, and on the dimension W. And when the network is uncongested, the cost of transmission of a new packet is minimal. When the network is congested, the cost of transmission of a new packet increases progressively with the degree of congestion. Social marginal cost, MCI, is the private variable cost KIT plus the externality cost, the second term here. That means if you increase the number of packages in the class I, QIT, that has an effect on the variable cost of all the other packages in the different classes, all the classes I until 1 until n. Now, when we now look at the externality cost, we have intra-class externality cost that is the effect on the other packages in the same class, and we have interclass externality cost of class I to subsequent classes I plus 1 until n, because due to the strict priority of quality classes, we have already a structure in these externalities, and the interclass externalities are top-down, one-sided. Only upper classes upper quality classes cause interclass externalities to lower classes, but not vice versa. When you look at the queuing model, all the red packets are served first, then the high priority, then the medium, and then the low priority. Marginal externality cost of delay imposed by class I traffic to the traffic of subsequent classes, I plus 1 until n, that are the interclass externality costs. Now when we look at the optimal pricing and capacity choice rule, maximizing, let's say maximizing the profit with respect to the number of quantity of number of packages in the different classes and the dimension. We have the revenue over the different classes and over the time, and minus the cost, the variable cost, KIT times QIT, the sum of over all classes, minus the sum over all time periods, of course, minus the investment cost, rho W. And then we have the optimal congestion fee for packet transmission in traffic class I, consisting of intra-class and interclass externality cost. Intra-class, the congestion, let's say the congestion fee is the difference between the cost price minus the variable cost. That is, the first term is here, that are the intra-class externality cost with respect to the same class, and the second term is the interclass externality cost. And of course we have the optimal investment rule, that the marginal cost of an additional capacity unit must be equal to the sum of marginal benefits for users of reduced congestion on the different traffic classes. Left side is the marginal cost of extension, and the right side is what is its value to extend marginally the bandwidth, what congestion will be reduced for the different packages, the different classes, and that is the optimal investment rule. Now, the question is, what about which kind of pricing would be, let's say, would be a good starting point to have to take into account the opportunity cost of package transport in this kind of environment. The congestion fees based on interclass externalities based traffic class prices are monotone, and the lowest best effort traffic class has a package transmission price of 0. When we have transmission package prices, it is interesting that usually in congestion pricing, when you have a highly congested network, the price is high. When you have a very low congested network, the price is low. Here, the interesting thing is that in those class, in the highest quality class, where you have nearly no congestion at all, because you have high priority, you have to pay the highest access charge. And this is the reason, because the opportunity costs you are creating for the packages in the subsequent classes are taken into account as a pricing criteria. That means the interclass externalities are highest when you are in the highest class, because then you have an additional package Q1T in the highest class has a lot of interclass externalities QJT for all the subsequent classes 2 until n. And when you go down to the last, also the second last class, T minus 1, tau minus 1, has only effect, an additional packet in n minus 1 has only effect to the last class, QUN, and that is monotone, so that you have a decreasing price sequence when you use interclass externality as pricing criteria. And so the price differentiation according to interclass externality pricing provides incentive compatible prices, because if the high priority class would have to pay lower than the medium or the low priority class, it would not be incentive compatible, but this here is incentive compatible. Users with higher preference for priority traffic services have the possibility to choose a higher service class and thereby pay a high price for high quality, less congested traffic services. Its advantage is that important elements of congestion pricing are included. High priority users have to compensate for additional traffic delay imposed on lower classes. These opportunity costs can hardly be ignored when establishing competitive pricing strategies and should therefore survive under competition and free entry in the internet traffic markets. There is in the current debate something what is called the dirt road fallacy. And the dirt road fallacy, the claim of the dirt road fallacy is that this kind of quality differentiation would create ad hoc discrimination between high quality and low quality users. But from my point of view, that does not take place, because market-driven network neutrality provides incentives to internet traffic providers to offer a consistent choice of user charges and capacity allocation that will be simultaneously determined when you have users when you have a population of users which needs very much high priority, then more capacity is used for the high priority. When you have a population of users which have strong preference for low priority services, transportation services, then more capacity will be used for this low priority service. So that is endogenously determined. Capacity is extended to the point where the marginal cost of an extra unit of capacity is equal to its marginal benefit of reduced congestion within the different traffic classes. Since the allocation of capacity to the users of the different traffic classes results endogenously, incentives to implement application restrictions disappear. That is, let's say, a more sophisticated instrument to bring efficient allocation of transportation services. And now we have, of course, the problem that when we have economies of scale in extension of capacity, that this marginal cost pricing need not necessarily cover the total cost. And therefore, of course, one can think about markups on the interclass externality cost. I would say that is also in the spirit of, let's say, market-driven net neutrality. So as in other markets, also when you have as reference points the interclass externality, that means the true opportunity cost, that then you start and add, let's say, for example, a markup to cover the total cost, endogenous transit pricing or two-part tariffs can be applied, but that would, let's say, market-driven also, I think, let's say, I would say that is not in contrast to a market-driven net neutrality concept, as long as you are taking into account the opportunity cost of transmission by interclass externalities. And so that is alternative forms of this pricing. Another question is, of course, what happens with the last class? Should the last class, which has no interclass externalities, should that be for free, or should this best effort class, or should it have also a price? It could be a price that would be a price on interclass externality for the best effort class, because one could argue quality guarantees as substitute for intraclass externality pricing do not exist in the final class, because the relevance of intraclass externalities diminishes if sufficiently high quality guarantees in upper class are implemented. But since in the lowest traffic class N, no quality guarantee is provided, interclass externality pricing may be applied to solve the allocation problem of packet dropping and social inefficient delay. And of course, a final check has to be if a carrier would introduce intraclass externality pricing in the last class, is it still monotone? Is it still incentive compatible? And that is what one can show. That is, otherwise one could not propose to have interclass externality pricing in the final class. And why is that the case? The interclass externality price in class N is always lower, this can be proved, is always lower than the interclass externality price of class N-1 due to the top priority scheduling. An additional package in class N-1 causes a larger delay on the packages in class N than an additional package in class N. That is so because when you have a queuing model, you look at, assume you have only two classes. The red packages have to be served all four. When you have an additional red package, then all the packages in the subsequent class will be delayed. But when you have an additional package in the final class, then only, let's say, if it is because it is randomly equally distributed, you have only the expected value, that is half of the maximum. That means it must always have a lower delay when you have an additional packet in the final class than an additional packet in the class before. So that the monotony of traffic class prices is guaranteed, and it depends, of course, on the strategies of the network carrier, whether he would introduce inter-class externality pricing. For the internet community, I think it would be a fine feeling to have at least one class without paying something, but I would, as economist, not argue in favor of that. There was already the question of transaction costs between the different carriers. That is a separate part in my paper, the role of quality-based interconnection contracts. And here we know that increasing congestion and asymmetric traffic flow results in more complex contracts among different network carriers. There are already new forms of interconnection arrangements, for example, increasing role of partial transits with subset of networks, increasing role of paid peering, increasing role of secondary peering arrangements already since years. There's also good literature on that. But these instruments, these tools, are all based on average quality. They are not based on quality differentiation. All these nice articles, when you look at in La Fonte-Roth's book in 2000, they were just saying that would be really a good step for research for the future to introduce quality of service differentiation. And that was at that time when this work on secondary peering and partial transit was developed, only one homogeneous quality. And the idea is now the increasing need to bargain on quality-based congestion charges within internet interconnection arrangements. And there are, of course, alternative approaches. Global universal quality-based service level agreements. I do not see how one can find them so immediately to get the whole internet community on such quality differentiation arrangements immediately. I do not expect that. And the search for a global quality standard scheme, I would say at least one would need to have different internet architectures comparable. It's also not easy. There are high transaction costs of implementation due to the large number of participants involved in global bargaining. And finally, what I am arguing coming from Freiburg, the evolutionary search for bilateral and multilateral quality-based service level agreements, which means incentive-based service level agreements by means of inter-class externality pricing. We know that the peering arrangements were always so that it is a Nash equilibrium that you offer the lowest quality. That is what the situation is. But when we have now situations that we pay for the compensation of the opportunity cost to provide premium services, and interconnection charges according to interclass externalities are incentive compatible because compensation of the marginal congestion cost of delay imposed by premium class traffic on the traffic of subsequent classes is provided. One has to have an instrument. One has an instrument to offer the peering partner an arrangement, or the transit partner an arrangement that he also brings. He will be compensated for higher quality services. That is. Thank you very much.